Okay, section 3.3, we're looking at properties of functions, and really in this section just looking at a few different properties of functions, learning some new vocabulary, and going to be looking at some graphs. And so we're going to look at what's called even and odd functions and see what those are. We got a couple of different ways we can determine exactly what an even or an odd function is, and so we'll be looking at that. And we'll also be looking at some pictures of graphs to see where they're increasing, decreasing, or constant. And kind of based off of that, we can then look at local maxima and local minima, and then from there go on and do average rate of change of a function. And so really a lot of this is vocabulary and dealing with these graphs. And so first let's look at even and odd functions. One way to interpret even and odd functions when we're looking at a graph is just by using some of that symmetry we looked at in one of the previous sections in chapter 3. And so when we say even and odd, that actually can describe a couple of those symmetries we looked at. And so we'll come back to these precise definitions in just a second, but here's what I want to look at first is this couple of statements here. It says a function is even if and only if its graph is symmetric with respect to the y-axis. So that y-axis symmetry we talked about before, if our graph has that symmetry, then that means that function is even. And then if we want to talk about an odd function, it says function's odd if the graph is symmetric with respect to the origin. So if it has that rotational symmetry, then that means that function is odd. And every function we look at is either going to be even, odd, or neither. And so so even, odd, or neither, those are the three options. If it's even, it's not odd. If it's odd, it's not even. And then, it could be neither one of those. So some examples, it says determine whether each graph is even, odd, or neither. I'm looking at this shape right here. This is that parabola shape. If you'll notice, it does have a y-axis symmetry. You can imagine if you were to look at this y-axis right here, and we have that mirror image of the graph there on the y-axis. So this does have y-axis symmetry, which means it is an even function. Okay, we'll call that an even function. Okay, the next one, whoops. This shape right here, notice it's definitely not symmetric with respect to the y-axis. We don't have a mirror image happening there, so it's not an even function. This graph also does not have that rotational symmetry. If you were to rotate this graph, you'd have to go a full circle before it would line back up on itself. So it's not symmetric with respect to the origin. So if it doesn't have either symmetry, we say that this is neither. It's not even, it's not odd. And then lastly, this graph, if you'll notice this graph, I can actually take it, and if I rotate it a half turn, isn't that the picture I just had? Compare that to this right here. So that is a rotational symmetry. Symmetric about the origin. So that means this is an odd function. Okay? And so that's one way we can tell if a function is even or odd, just by looking at its graph and looking for that symmetry. And now that's not the only way we can answer that question. If we'll go back to these definitions up here that we skipped over a second ago, we have what's called an algebraic definition. This says a function f is even if for every x in the domain, the number negative x is also in the domain, and f of negative x equals f of x. So this statement right here basically means if you take and plug in like say you plug in f of 2, it's always going to be the same as f of negative 2 for that particular function. Or you could say that maybe f of 3 is the same as f of negative 3. So it doesn't matter if you plug in some value or its opposite. When you plug it into the function, you get the same result. If that's the case, we call that even. And then a function is odd if f of negative x is equal to the opposite of f of x. So say maybe for some function f of 3, for whatever that function is, maybe it's equal to 27. And then for f of negative 3, if we plug in the opposite, we get negative 27. So here, f of negative 3 is the opposite of f of 3. So we call that odd. So it's a little bit trickier using that definition. This would be the algebraic definition. If it says determine algebraically whether it's even or odd, like this example right here, determine algebraically whether the function's even or odd or neither. That's where we use these statements right here that we just covered in those definitions. And so let's see, how would you do that exactly? Okay, the first part A here, we've got f of x is x squared minus 5. Now if we want to determine algebraically, well, let's see first if this is even. So if it's even, f of negative x should equal f of x. Okay, so here's f of x. This is f of x right here. We want to know, compare that to f of negative x. If this is even, then f of x and f of negative x should be the same. Okay, if we do an f of negative x, that's squaring a negative x. Okay, just plugging in negative x for x. And then if you square that piece, that's just going to make a positive, right? So f of negative x is x squared minus 5. We can simplify that down. Now if you'll notice, these two, aren't those the same? So in other words, f of x, this guy up here, is the same as f of negative x, this guy right here. So in other words, that's what this statement right here says. Those are the same, then that means this is an even function. So without looking at a graph or anything, we could determine that's even because f of x is the same as f of negative x. Okay, next one, x cubed minus 1, g of x here. Let's look at g of negative x, see what that is. That would be a negative x cubed minus 1. If you cube a negative x, that comes out negative, right? Negative times negative times negative. So we get negative x cubed minus 1. Now comparing these two again, are those the same? Well, no, because this is negative, this is positive, so they're not the same. So they're not even. This function's not even. Maybe it's odd. What does odd say? Okay, f of negative x should be the opposite of f of x. Well, the opposite, in this case, of g of x would be the opposite of the whole function, right? Which is, if we distribute that negative sign, negative x cubed plus 1. So are these the same? Well, no, because that's a minus 1, that's a plus 1. So these two didn't match, so it's not even. These two didn't match, so it's not odd, so this one must be neither. It's not even, it's not odd. Okay, last one. First, let's look at h of negative x. So 5 negative x cubed, whoops, minus negative x. Okay, cube at a negative x, that result's going to be negative, and then minus a negative makes a plus x. Comparing these, remember this is h of negative x. If you compare these two, are they the same? Not the same, right? But notice if you do the opposite of h of x, again, distribute the minus sign. Don't these match? So h of negative x does equal the opposite of h of x. So that is odd. Okay, so that's how you can determine algebraically whether it's even, odd, or neither. I do want you to know that you can also, again, look at the symmetries of the graphs. Just real quick to demonstrate that, I'm going to graph x squared minus 5. And if you'll see there's that parabola shape. Isn't that symmetric with respect to the y-axis? Okay, we see that. Again, doesn't that mean that it's even if it's got that y-axis symmetry? So we see that. Then we can look at x cubed minus 1. Notice there's no y-axis symmetry, and also the rotational symmetry is not there either. So neither symmetry means it's not even or odd. And then 5x cubed minus x. Graph that real quick. And just so we can get a better picture of what's happening here, I want you to see that symmetry. I'm just going to zoom in right there on the origin. See that rotational symmetry? If you rotate this a half turn, you get the same picture. That does mean it's odd. So the symmetries are all there. And for even, odd, and neither, that's a concept that's really important in calculus. Something you'll use if you eventually take calculus later on. You'll talk about even, odd functions and get some more use out of that concept later. For us, we're not going to really do much beyond identifying those. Again, this is just something that you'll use later on. Oh, I got one more here. Absolute value x. Forgot this example was here, so let's work that real quick. So plugging in, hopefully you guys kind of know the drill by now. We're going to start out by looking at f of negative x. Now if we're doing absolute value, negative or positive, isn't that going to be the same as the absolute value of x? You know, just like if you do the absolute value of like negative 3 and positive 3, it's both 3, right? It doesn't matter if it's positive or negative, it just comes out positive here. And so f of negative x is the same as absolute value x, which is f of x, right? And so this one would be even. And again, if you look at the graph here, the absolute value of x, don't you see the symmetry? Y-axis right there. So that means it's even. Okay,